This meeting is being recorded. All right, so yes, this is the last lecture before the exam in dos dios. Tristan, can you translate that for me?
Yeah, you just said in two gods.
Oh yeah. Well, you know, dias is what I meant to say, but you know.
Yeah, there you go.
That was. Can we start this meeting over so that's not recorded? Because you're right, I completely. I'm an idiot.
No, I'm on board with this whole like having the exam between two gods.
Yes. One is named Janice. Okay, so anyway, in 2 days, we're going to have this exam, and it will have this last little bit. It's not a big deal. What we're going to do is just reinforce some pH-controlled solubility, talk about what amphoterism is, and call it a day. So this might actually be a shorter lecture, and I'll answer some questions afterward. As far as the exam goes, I am, quote, working on it. In what I mean by that is I didn't get a chance yesterday to talk to my gurus, but when I did the Chem 110 exam, which was a written out one, I made a PDF of the exam. I posted it as a quiz because you can't do it as an assignment. I had to do it as a quiz. You had to download it and you had to write it out, take pictures with your phone, and upload a PDF to my email. That's what I'm trying to fix. I'm trying to make it so that you can upload it to an assignment because a quiz does not allow you to upload a file from what I can see, but an assignment does. And so I need to find a way to combine the quiz, which allows for a timed aspect of the exam over a certain window, whereas assignments do not. I have to couple that quiz that is timed with an assignment that's not timed. However, it allows you to upload an assignment. Does that all make sense?
Yes.
Good, because it doesn't to me yet.
Could you like just make an assignment and then attach the quiz, but then, or sorry, the PDF, but then make the assignment due like in a certain amount of time?
Well, so I thought about that, Kimchi. Now, actually the best way of doing that is I would say make an assignment. I'll make it go live at 9:30, and by 11:30, I make it go dark. And if you haven't turned in your stuff, then you're hosed. I don't want to do that because what if someone has internet difficulties, and what if someone has recently planned their life around not being here at 9:30? Looks like half of the class at least is doing that. So because it is kind of online-ish, I don't want to pigeonhole people to a time. Hence the quiz, where you can have an open window of say 4 hours or so to take this, and within that 4 hours you got a couple hours to do it and get it uploaded. So that's the reason why I'm trying to do a combination of the two. So I'm working on that. I'll have a little more about that. There is something called, what was it called? Chem
Scanner.
Chem Scanner. One of my Chem 110ers. That was you, Melinda, right?
Yeah.
Yeah. One of my Chem 110ers showed me that she could take 6 pictures of whatever she had on her phone and use this Chem Scanner app to make one PDF file. It apparently automatically sized it to reasonable size for me to, with my wonderful 5 megabytes download speeds, to actually download the PDF so I could grade it. So I highly recommend
just download
this Chem Scanner, and I will put this in an announcement for everyone with some instructions. The other option, of course, is you can take pictures with your phone. You could email them to yourself. You could print those to a PDF and make one PDF, one PDF, and then upload it that way. I'm also going to try to keep this uploaded into Canvas itself. When I tried this with my 110 class, even though you're smaller, I was getting 80 emails from my students, and usually more, because they're like, oh, did you get it? Did you get it? Did you get it? So I had easily 100 emails in one day. On top of all the other emails I was getting, it was very difficult to keep straight which ones had the files and which ones didn't, and I've had to have 2 people resubmit as a result. So I'm going to try to do it in Canvas so Canvas can at least keep track of it for me. Let's see. I will also have instructions in the announcement of how I want you to name the PDF so that when I download it, there is some rhyme and reason to that naming so I don't lose it. Some people just put exam PDF and I'm like, all right, who are you and what's going on? So I'll have some guidelines there. Any questions so far about that?
So do you want this one done explicitly by hand?
Oh yeah. Yeah, so I know Dallas, you're a big fan of doing your homeworks with the typing out stuff. Yeah, you got to do this by hand. There's no way to do it otherwise. And let's see. Of course, I trust you guys not to do anything nefarious. And I will probably, oh yeah, that's the other thing. I plan to actually have a Zoom meeting open. And I will have a chat window open. And if you have questions, you can send a private chat message to me. And I can privately answer your question. Does that make sense?
Yeah. Yep.
Melinda, am I missing anything from the Chem 110 aspect?
Not that I can think of.
Okay. Hey, where's Boudica?
She's not feeling well.
I was gonna say I texted her, but I haven't got a reply.
Took her a
Okay.
while to reply to me.
That's how sick she is. She can't even reach her phone. All right. So do we have any other questions? Seeing none? That never gets old. Let's see if I can get this chat window over there. Okay, that's gonna be my border. All right, let's continue the pH controlled solubility. Let's see. I want to, oh, let me get my glasses. Glasses, where'd you go? There you go. Apparently I need glasses for everything now. Tristan, quit laughing at me. Control solubility. Zinc carbonate with pH. Now, as I mentioned last time, sulfides and carbonates are the two good ways of controlling solubility. Sulfides are stupid good at precipitating things out. Carbonates are fairly good. Carbonates actually have a little bit better range over which you can try to control the solubility. So we're going to look at that. The other nice thing about them, and I'll show you this as we get to the equations, I'm going to write out the equations and note one of the last ones there for you. So we know that we have zinc carbonate. Oops. We have zinc carbonate. Goes back and forth to give us zinc ions and carbonate ions. And this has a KSP equal to 1.6 times 10 to the negative 16. So pretty insoluble. Now, one of the reasons why we like using carbonates and sulfides is the following. Because we have CO2 plus H2O will make H2CO3. So what this means, much as in the case of taking hydrogen sulfide gas over the water and creating hydrosulfuric acid, we can just bubble carbon dioxide through here. Now, again, with that lab that we weren't able to do with the carbonic acids, would have been a great one to see this, because what you would have done in there is you would have generated a whole bunch of carbon dioxide gas, bubbled it through water for a few minutes. As you bubble it through the water, you will essentially start to saturate the water with that induced dipole interaction. As long as you keep bubbling it through, you will do that at atmospheric pressure, because you're not going to pressurize anything if it's allowed to bubble. So what is really nice there is that this carbon dioxide here bubbles through at 1 atmospheres worth of pressure. And over the course of just a few minutes, you can actually saturate that water to make the most concentrated carbonic acid you can without pressurizing. This actually has a KEQ equal to 0.034. So it's actually a pretty good equilibrium as far as being able to go both ways, which of course is why once you are done bubbling through and bubbling through and bubbling through and saturating it, fairly quickly it's going to try to lose all that excess carbon dioxide that was in there and go back to just being water with the carbon dioxide going out. Once you generate that H2CO3, it will go ahead and set up its equilibrium of an H plus and an HCO3 minus. This has a Ka1 equal to 4.3 times 10 to the minus 7. And of course, that HCO3 minus can set up its own equilibrium of H plus and CO3 2 minus with a Ka2 equal to 4.7 times 10 to the minus 11. Now in this, we could have actually grouped both of those two together if we wanted to make our life easier. And so for Garrett, grouping these two together, what ends up happening?
The cross thing.
The cross thing, right? Where we say the quote cancel out, but we know that they're not canceled out, they are there, but in an overall reaction, they would be subsumed. So we could actually rewrite this. Rewrite this as H2CO3 goes back and forth to make 2 H pluses and a CO3 2 minus, where now remembering since we added them, it is Ka1, Ka2. Okay. Now, what's really nice about this is, and I just want to make it clear what we're doing here. We want the solubility of this zinc, right? That's what we're trying to do. In there, we know what the KEQ is, or the KSP, which means we essentially have two unknowns here, but this carbonate right here can be written in terms of the carbonate down there, or down there if you really want to get to it. So what we're trying to do here is get everything in terms of the carbonates to put them back up in there to solve for it. So let's go ahead and do that. Let's solve for concentration of CO3 2 minus in terms of the H plus and plug into KSP equation. Just to remind ourselves that that KSP is equal to the concentration of the zinc times the concentration of the CO3 2 minus. Now, since KSP is just a number, we could actually solve this out to say that the concentration of zinc 2 plus is equal to the KSP over the concentration of the carbonate. So once we solve for that carbonate, we can put it in here. The KSP is just a number. Hopefully everything else falls out, and we will end up with zinc in terms of H pluses. So we're gonna come back into this guy. But what I need to do is to get the carbonate. So I'm gonna go back up to this purple guy. And I'm gonna bring it down here, and we're gonna solve that for the CO3 2 minus. Ka1 times Ka2 is equal to the concentration of H plus squared times the concentration of CO3 2 minus all over the concentration of H2CO3. Is everyone okay with what I just did there?
Yeah, real quick. When you put KSP equals concentration of zinc 2 plus times CO3 2 minus,
Yeah.
you didn't take into consideration the zinc carbonate?
And why don't I?
I don't know.
Because it is a solid.
Ah, okay.
Remember, solids and pure liquids don't matter,
Gotcha.
right?
Got it.
So, and in fact, I'm going to go ahead and point that out because as we look at the H2CO3, right, this guy, you know, is the CO2 plus H2O goes back and forth to make H2CO3, and that had a KEQ. Well, that KEQ is equal to the concentration of H2CO3 all over the pressure of the CO2 times the concentration of water. Right? You okay, Chef?
Yeah, I'm good.
Okay. But remember, this pressure was 1 atmosphere. And what do we do to the water? We get rid of it. So this means that the KEQ is equal to the concentration of the H2CO3 of 0.034. So that now just becomes a number.
Can you go up?
No. Who said that? Isa?
Kimchi.
That you, Isa?
Kimchi.
Oh, it's kimchi. Where,
Yeah.
How far do you want me to go up?
A little bit more. The
Okay.
college called me just now, and I was talking to them. So, thank you. Okay.
Oh, so we should stop the lecture and go back just to catch you up. I don't know why you want me to scroll up. What do you need here?
No, I was just copying it down. I just like wasn't
Okay.
even writing anything for like 10 minutes because the college called me. Sorry.
What did they call you?
They just wanted to know how I was doing.
Yeah, we're actually doing a lot of outreach right now because apparently the powers that be think that everyone is descending into chaos, and you know, so I guess we're doing wellness checks, if you will. Who from the college called you?
I'm not sure what her name was. She was a counselor though.
Wow. Well, that's very nice, I guess. You're loved. All right. So are you caught up now, Kimchi?
Yeah.
Okay. So now what we want to do is solve this for the carbonate, right? That's the thing we're looking for. So we're going to say that the concentration of the CO3 2 minus is equal to Ka1, Ka2 times the concentration of H2CO3 all over the concentration of H plus squared. So now that we have that, we're just going to plug that right back into this guy. Is going to go whoop, right into there. Which means the H pluses are going to go on the top. Put into the zinc equation. So the concentration of zinc ions is equal to KSP, I believe, KSP times the concentration of H plus squared all over Ka1, Ka2, concentration of H2CO3. Yep, that looks right. Now, as we do this, hopefully you guys see that this is just math. And it's just a substitution, it's just like the mechanisms. But keep in mind that KSP, Ka1, Ka2, and this H2CO3 are all constants. These are all just constants. Therefore, they're just a number. Now, if you plug all that in, you probably end up with something like 232.8 times the concentration of H plus squared. Now, is everyone cool with what I just did there?
Depends. Can you tell us what the KSP was?
Oh, didn't I? 1.6 to the negative 16.
But I missed that.
Oh, so Dallas is checking my math. Okay. So while he does that, I want
What was
to
the value?
1.6 or 1.6 to the negative 16.
All right, thank you.
Not a problem. So I want to compare this to iron 2 carbonate. So iron 2 carbonate goes back and forth to make iron 2s and a carbonate. Now, hopefully, you might notice something about this equation and the zinc equations. Is there something cool about them? Tristan, are they lo mismo?
Yeah. The only difference is iron takes place as zinc. Same charge.
Yes, does everyone see that? Yeah, exactly. It's the same charge, it's the same system. I would solve everything exactly the same. Chef, are you okay with that?
Yep.
Isa, are you okay with that? Is Isa here? I'm gonna see who's here. Lion Lee, are you okay with that? I can do all the math if anyone wants me to, but I want to just see if anyone just realizes that it basically becomes exactly the same. Chad?
Wait, but doesn't iron have that thing where it can act differently depending on what it's bonded to?
That is correct. It could be a +2 or a +3. I told you that this happened to be the +2 version.
Julian, can you do me a favor? Can you bring me water? Actually, never mind.
I'd bring you water, Stephanie, but
Oh shoot, I'm on.
I'm a little far away. It's okay. I think it's funny.
Thanks.
All right, so basically, it looks like no one really cares whether or not I do the math. So I'm not gonna do the math. I'm just going to note this.
Tanaris said to do the math.
Who said to what?
Tanaris said to do the math in the chat.
I didn't hear him.
He wrote it in the chat.
Why is he writing? I want to hear his dulcet tones.
Probably doesn't have a mic.
Yeah, he does. He just doesn't want to talk
Had
to
a
me.
mic in a previous class.
He's talked to us before. He's doing passive aggressive right now.
Horace,
Yes.
I'm
His
a little
headphones are busted.
confused. I get why you did it, but not really. Why you brought in like the CO2 equation.
Yeah. Who's this? Kimchi?
Oh, yeah.
Okay, so why the CO2 equation? Okay, so the whole goal of this, and let me just see if I can get these three right here, 3.5, because as I combine them. The reason why I'm doing the CO2 plus water to make carbonic acid is because basically that's how you make carbonic acid.
Okay.
And by making carbonic acid, you can actually make the carbonate. Now, the really nice thing about, again, the hydrogen sulfide and the carbonic acid situations is the fact that you can control that equilibrium just by constantly bubbling the H2S, or in this case CO2, through the solution.
Mhm.
Because we're not pressurizing it, we are bubbling it through at 1 atmosphere's worth of pressure, which makes math really nice because the number is 1. It also means that as I'm constantly bubbling it through, I'm constantly regenerating any H2CO3. Any H2CO3, I don't know if, can you guys see my cursor moving?
Yeah.
Okay, any H2CO3 that decides to break up and become H pluses and get all the way down to the CO3 2 minuses, which are the things that are going to be spit off or consumed, depending on which way the solid equilibrium is going. If any of those happen to disappear or increase, this equilibrium up on the top will adjust accordingly
Okay.
to make sure that this equilibrium right here of the O34 is maintained. And it's very sort of singular to the carbonate and the sulfide systems,
Right.
because we have a gas that we can bubble through within that. And it really comes down to is this bubbling of gas that is constantly being maintained, which is constantly maintaining the H2CO3 despite whatever happens down here.
Mm-hmm. So if it was like US, or well, it was like zinc S, I don't know.
Then I would not use the carbonate.
Right, you would do H2S, right?
That is right.
Okay.
Yeah, and those are the two workhorses of this. I'm sure there are others. I've just decided to not even investigate those because these are the ones that in every book are there. And I'm sure you can make other systems where, I don't know, selenides. Of course, you could bubble hydrogen selenide gas through there, and you could figure that out. But most people don't like to work with hydrogen selenide gas because it's ridiculously nasty. Hydrogen sulfide is bad enough, but very useful for pulling things out of solution. And carbonic acid, forget about it, we drink it. So these are the reasons why the sulfide and the carbonate tend to be the workhorses, because they're the ones that can be used in industry safely and effectively. Does that answer your question, Kim?
Yeah.
Okay, so I want to compare this to the iron 2 carbonate, and I'm going to go ahead and note, just for the people not here, note, all math will be the same. Only the KSP value will change. And before you say it, Dallas, the KSP here is different. And it is going to be 3.13 times 10 to the negative 11. So the other one was 10 to the negative 16. This is 10 to the negative 11, which means what? Not Dallas.
It's more soluble.
Yes, it is more soluble. I know it is weird for us to be like, well, 10 to the negative 11 is like stupid, not soluble. Well, I'm not asking you whether it's soluble or not. I'm asking you, is it more or less than the other one I'm comparing it to? And negative 11 is much bigger than negative 16. So I always like, and who said that, by the way? Was that you, Melinda?
No, it was Kimchi.
Okay, I'm going to pretend it was Melinda. So, no, it's really good insight to think about this in terms of like, since it's a comparison, you don't want to look at just the number, which as you look at it says, wow, that's really not very soluble. You'd rather want to look at it between the two. So as we do this, and as we go ahead and quote, do this math, I'm going to go ahead and do this in I guess, orange. No, I'll do it in red. Wait, what was the last one? Oh, is it green? Oh, I'll do it in blue. So iron. So that would mean that the iron 2 plus is equal to, once you do all the math, by the way, it is 3.99 times 10 to the 7th times the concentration of H plus squared. I just plugged it all in. Dallas will check my work for me.
I already did check your work, and I'm getting something different.
Go on.
And the zinc one, I got the same answer as you. So.
Did you use the same Ka1 times Ka2 in the 034?
Yeah.
Can someone else confirm? Because no one else has challenged me until Dallas. I don't know why you challenge me so much, Dallas.
Because I live for the fight.
I love your honesty, Dallas. Anybody else confirm?
I got 4.55 times 10 to the 7th.
Yeah, that's what I'm getting.
Yeah, I got that as well.
What? In all these years, no one has challenged me. This is so funny. What'd you guys get?
4.55 times 10 to the 7.
That's weird. Let me fix my notes. This is why I normally just let you guys do everything for me, just in case. No, 4.55. All right. Well, it just so happens that that won't matter for what I did for you. What I did is I ended up going ahead, and you guys will see this here, and I plotted them. I made a nice little chart here where I did pH from 0 to 14, figured out the H plus concentration, and then I plugged in, I don't know if you guys can see this, but I plugged in my value up here of 232.8 for the zinc. Oops, don't do that. Is there an escape button on this thing? Shoot, don't do that.
Hit the reverse.
Do what?
The reverse arrow. Maybe?
All right, thank you. Thank you. So I'm not going to go through the rest of it. I plugged in the other equation for the iron. And do I just have to hit that? Okay. See, this tablet is not very good because you don't have the keyboard up. Anyway, so I plotted it for you guys. And hopefully you guys can see here that it ends up, and this is solubility on the left and pH on the bottom here, and I'm comparing the two of them. And the zinc here is in blue and the iron is in red. Can you guys see all that?
Yeah.
Okay. So if you were to try to control the solubility, and let's say that you were in neutral water. Over here, you can see my cursor here in pH 6, 7. Both of them would essentially be out of solution. You see there's like nothing in solution. But if I were to slowly start making it more acidic and more acidic, somewhere around pH 3, my solubility of iron skyrockets. And yet my zinc is still sitting at 0 concentration. And so as you get through there, I wonder if there's a way if I can draw. Can I draw a nice little line here? Ooh, I could use my pen. Bam. So if I were to say get give me the pen. Get to a pH, say right here, this means that the iron is soluble, but the zinc is not. And this is how you can control which metal is still stuck in solution and which one comes out. I think that's kind of cool. All right.
So what if you wanted to get the iron out but leave the zinc in?
Well, so define get the iron out and the zinc in. Well, so what I could do here, let's say that I want to get the iron out but leave the zinc. Well, I could do exactly what I just did here. I could make sure the iron comes out of solution. I could take all that eluent and put it off to one side, leaving behind all the zinc. Now I have two solutions, one that is all zinc and one that's all iron. You want the iron out but not the zinc? Well, take the iron and make it neutral again. All the iron's going to fall out. Take your zinc solution that you separated out and just start acidifying it, and bam, your zinc is in solution. So
Right.
it's not that you would want them both around at the same time and somehow magically flip which one's going to be more soluble, but rather you would precipitate one out, carry off everything that is soluble, and say, okay, you guys go downstream, and I'll put you in a bucket. Hey, all you guys that were still sitting at the bottom of this bucket, stay there. Let me acidify you. Now you're in solution. Does that make sense, Dallas?
Yep.
Can you go back to your like numbers?
Oh, the numbers? Or
Yeah.
that? This?
The numbers for the graph.
Okay.
So
Now
you're
I'm gonna
just
have-
go ahead. You're just changing the concentration of H plus.
Yes.
Okay, just checking.
So if I look here, I don't know why I'm still on a draw thing. I want to get off the pen. How do I get? Let me get back to the select tool. If I go in here, you can see that I have that normal number, and here I'm referencing now the H plus concentration and squaring it, just like our equation. And I did the same for, oops, just undo that. And I did the same for the this guy right here for the iron, where that's that 3.99. It should be 455, but whatever. It's not going to matter for the plot. But so I just did that, and again, I referenced the H plus concentration squared.
Can you include that on the notes in Canvas?
It's been recorded. Oh, you want me to do the plot?
No, I didn't know if you could like attach. I don't know.
I can do this. I can. I wonder if I can just copy this whole thing. Copy. There, like that?
Yeah, thank you.
You mean like Awesomevilles? All right. Well, ask and you shall receive, Chef.
Thank you.
All right. This is my last example for the pH-controlled solubility. Any preguntas before I do the last little idea?
Yeah, I have a quick question for us.
Good.
So in all of our examples so far for this topic, we've shown that whether it be zinc or like iron, is dependent on the concentration of H plus, but we never actually solve for H plus and get the actual like number. In the homework, there was a
in the homework it
problem.
says,
Yeah.
yeah,
And
in the homeworks there'll be questions of like, what is the solubility at this pH,
yeah.
right? Well, you just stick in that pH. So
Yeah.
what I mean by that is let me go back here. Once you have your equation, okay, once you have that thing, you could actually generate. And I will tell you guys this. I will not consider it cheating if you whip out an Excel thing and quickly program it and just let it go. But to that end, if the question, Tristan, is just to calculate the solubility at a certain pH, so let me go back to this guy. Let's say that I wanted the solubility of iron here at pH 10, right?
Yeah.
So Tristan asks, what if we're not making a plot? But the concentration of the iron 2 plus at pH equals, I don't know, let's not do 10, let's do 4, okay? Just so we get a reasonable number here. Well, the iron was equal to 4.55 times 10 to the minus 7. You would now do 1 times 10 to the minus 4 squared, because that's your H plus concentration. And if you do that, you should probably get 45.5, if I did my math right.
Okay, cool.
Does that make sense?
Yeah.
I'm getting 0.45.
Oh, I moved my decimal the wrong way.
Yeah.
Sorry. Oh, and because that's actually a positive 7, and that's a negative, yes. I knew I'd get something normal, so it's 0.455. Sorry. Thank you, Dallas. Yeah, because there are some homework questions that ask you, hey, what's the solubility at this pH? You wouldn't worry about making the graph or comparing like that. You just plug in an H plus concentration.
All right, cool.
Oh, Kimchi, it's going away. It's going away.
I got it.
Oh. All right. The last thing here is amphoterism.
Actually, can you just go back up?
¿Cómo se dice ay mis gatos en español?
You just said it in Spanish.
For up, Isa.
You're good right there. You can go back down.
I like how you know, you guys tell me to do something. I ask why, and they're like, oh, never mind. You just go back down.
It's because we want to write down stuff.
I'm like, what? Oh, okay. I thought there was a question. Okay. Oh, I'm good now. All right. Last thing is amphoterism. Now, amphoterism is a funny thing. So it is a funny property of some transition metals, not all. I know zinc does this, aluminum. I want to say cadmium does it too. There's definitely a handful of them that do this, and it's kind of fun. what it is when it is soluble in an acid or base, but not in between. Now, one of the more well-studied ones of these happens to be what is called the zinc-8 ion. And it's kind of a fun one. So, check it out. You have, I'm going to go this one. You have zinc hydroxide going back and forth to make zinc 2 pluses and 2 hydroxides. But the fun part about this is you could have this zinc hydroxide plus a couple of more OH minuses going to make this zinc OH4 with a 2 minus. This is called the zinc-8 ion. Now, of course, that's going to be a solid and an AQ and an AQ. So we're looking at that solubility. And of course, you have a solid AQ and an AQ. Now, I don't care what their KSPs are. I'm just pointing this out as the following. So we have these two equations. Let's get a shape. Let's do something like this. And I want another line. Let's make this nice. Okay. Now, what this means is if we look at pH, going from 1 to 14 nominally, we're going to have to do the Wayback Machine to talk about Le Chatelier. So at low pHs, do we have a high or low concentration of H's?
A high concentration.
That's right. Now, if we have a high concentration of H pluses, all right, so low pHs, high concentration of H pluses, not Dallas, not kimchi. Let's see, Kyra's not here. Low band. If you have a lot of H pluses, what's going to happen in the top equation?
The top equation that you
Yeah.
just circled.
Yeah.
If you have a lot of H pluses, isn't it going to be a lower pH?
Yes, but what does that do to that equation? Pro tip, Le Chatelier.
Doesn't it, oh, never mind.
Race in, Garrett. Race in. Help her out.
Does it grab onto the OH minuses and it's making water, right?
Okay, if it does that, then what?
It's losing H pluses or gain.
Gherkin, are you in here?
Or no, the pH is becoming basic.
Oh, man, you're so close. Alexia.
She's tired.
I don't know.
Okay. Kimchi?
Yes.
Oh, dear.
Sorry. So if you add H pluses, then you're gonna I mean, isn't the equilibrium gonna shift to the left?
Shift to the,
The right? Oh, the right.
why is that?
Because the H's attaching to the OH's are making that like smaller, so it wants to go.
Removing them, right?
Yeah.
So Garrett was on the right track when he said H pluses and OH minuses come together to make water. Well, if that's the case, then every time they come to make water, that goes away, which means the equilibrium now says the zinc hydroxide has to continue to break apart. Remember the silver acetate, right? When you sucked out those acetates with the H pluses, the silver acetate had to break apart. And we said, hey, what's going on? The acid is not attacking the silver acetate, it is attacking the acetates themselves, causing the silver acetate to break apart to reestablish the equilibrium. So in that, when you start adding in more H pluses, they're going to suck out those OH minuses, make the equilibrium go to the right, which means your concentration of zinc 2 pluses gets very big. Now, you can imagine that as you have fewer and fewer of them, it will start to drop off. And so over here, you have a high concentration of zinc 2 pluses over on the acidic side. Is everyone okay with what I just did, Chef?
Yeah, I'm good.
Isa?
Yeah, I'm doing fine.
Meng?
Yep.
Linley? Linley? And he's probably getting a drink. All right.
Is there a problem that we're
More
missing that
coffee
you
for him.
want us to point out, or are you just
No, I'm
really
just making sure that everyone's okay and not having a little like I'm just going to be quiet and hopefully they'll figure it out on the side. I'm just making sure everyone's on the same board there, Dallas.
Wait, no, I'm
Okay.
Why don't you
Who's that?
show us show us the equilibrium, what's going on, and maybe that'll just clarify things.
Yeah, I
I
don't
did.
wouldn't the zinc concentration go up?
Yes. Do you see at low pHs? At low pHs, the zinc concentration does go up. Right
Okay,
here.
it gets lower, but as it gets higher, it goes down.
Right, because as you have higher pH, you have fewer and fewer H's
Okay.
to attack the OHs, so you won't shift the equilibrium quite as hard.
Okay. All right, cool.
Chef?
Yeah, that's fine.
Okay. Now what I want to do is I want to look at the second one here. If I go to higher pHs, my concentration of OH, is it getting more or less? Not Dallas. Alexia. Alexia.
I'm gonna say higher.
That is a good thing to say because as the pH gets bigger, the OHs are increasing. So if those OHs are increasing, what happens to that equilibrium that I've circled in blue?
It shifts left.
To the right is the correct answer. Does everyone see that? Garrett does not. Garrett,
I see it now.
you see it now? Right, because what we're going to do is we're going to overload on this side, causing it to shift over to the right.
Are you adding OHs?
Yes, I'm getting pH 14. I'm dumping a whole bunch of them in there, right?
Yeah.
So as I dump them in there, I'm gonna load up the left side, which means it's got to shift to the right. So that means that at high pHs, the zinc cation is produced. Hence why I have the two axes here. That also means that for both of them, as I start approaching the middle pHs, they basically don't do anything to that system and leave it with the solids. Now, how far above the ground that green line gets is all dependent upon their relative KSPs. And let's be clear that what I'm really not showing you is that the zinc is doing this while the zincate is doing this, and I'm just combining the two curves there at the bottom in the green. Now, I'll tell you, I'm not going to make you generate numbers for these things. I'm not going to do a relative, but what it like pH something, how much of one ion and how much of the other. Oh, wait, no, that's a good idea. Ooh, no, I won't do it. But you should be able to, describe in words to a normal person what it means for these guys to be soluble in one and not the other, and perhaps why. In case you didn't hear that rustling, that meant the last page of my notes had been put away. So that means you guys can start packing up rather rudely and leaving. It's okay.
Forrest, are you having office hours tomorrow?
I will have office hours every day. I'll be around at 1 today and at 1 tomorrow.
1 tomorrow?
Yeah, I will have another conference call at 2, however. So I won't have an open end on that one, but I could also be back a little later. So I'll be back at 1, and maybe even after that, depending. You can always shoot me an email and say, hey, do you mind if you pop on? Because I'll definitely be doing a lot of other work in the meantime.
Okay, thank you.
All right. So are we okay? Do we have any other questions? Or should I just stop recording?
Oh, that's it for this lecture? Oh.
That's it, man. I know.
I have one question concerning the test.
Ay, mis gatos. Kyra, first of all, this whole time I've been not calling on you saying, oh, Kyra's not here, and you've been here.
Yeah, I wanted to say something then, but my computer, I couldn't get it to unmute. But
do I need to share my screen again?
No, it's not concerning the lecture. It's just about the test in general. I
like roses. My grandmother gave me a bunch of roses to put around the property. Oh, that wasn't your question. Sorry.
No. So for the test, will you send out like an announcement with the test questions?
Were you here at the beginning?
No, I came in late, like at 9:50.
Well, maybe you should watch the beginning of this lecture. Walking in late. Let me guess. You couldn't find a parking spot?
No, my computer shut down.
I did like a good 20 minutes about sort of what's going to go on with the exam. So
okay.
just watch the beginning. It'll be up in a couple of hours.
Okay.
Zoom's been a lot better about getting them back to me in a couple hours, and I'll post it up.
Okay.
Any other Johnny-come-latelys that want to ask questions about stuff that we talked about already? Just saying.
Yeah, I have a question. I'm still not clear on why zincate ion is called an ion, because
okay. So that's actually it's a subtle thing. It's called the ion because check it out. You see that it's charged up here, right?
Mm-hmm. Yes.
And it's an aqueous. Anything that is a charged particle has to be dissolved in water, therefore aqueous, therefore it's an ion. Anything that's charged is an ion. Now, why they called it the zincate, well, I don't know. I decided not to look that up. I don't care.
All right, thanks.
Now you got to make me go look up why it's called zincate. Now, I'm sure there's some historical significance to that. But yeah, it's just the name of it, just like phosphate, carbonate, you know, you name it. They had to give a name to that compound when they noticed it floating around in solution. I assume they went with 8 because everything else had an 8 version on it. If you have a burning question, I just go to Wiki. I bet they'll tell you why it was named that way. But that wasn't really your question. Your question was, why is it an ion? And it's an ion because it's a charged particle. And they can only exist in aqueous solutions. Unless Dallas wants to give us a full lecture on plasmas.
I mean,
no, you're not. I was kidding, Dallas. I was kidding. Unless everyone wants to hear it. Anybody? Oh, yeah. Seeing no hands, Dallas. That was your one chance to take over this lecture.
damn, missed it.
Just did. Just like that one time that I could have asked Wendy. Oh no. Well, it just got dark there. I hope I wasn't recording that.
You were in fact recording.
Man.
Zoom's gonna have that in their database forever now.
Right? I can actually go really dark, but I won't.
Maybe you should stop recording.
Oh, maybe I should stop recording.
Remember, Forrest, these are all chaotic times for